Hey everyone, my name is Taylor Sparks, the editor-in-chief of IMMI. I've got a new paper on uncertainty quantification, and it comes from my friend Aaron Tallman, somebody who I consider one of the experts in uncertainty quantification. So when he sent me something about stochastic plasticity using profilometry analysis of AL7075 that's cold sprayed, I was a little bit curious. Now, why? Well, if you've done additive manufacturing, then you've probably seen these sort of arrays of indentations. They look like this. Totally typical, right? A bunch of different indentations. They do a bunch of these things. And normally what you want to see out of that, or what they'll report out of that, is maybe the average hardness and the standard deviation, right? That's typically as good as you get. Aaron's going to do something quite a bit more in depth. It's called residual analysis. So he begins the paper by pointing out that plasticity in these localized neighborhoods of grains can dramatically impact part performance, especially if it happens to be in a spot where there's a geometric stress riser. And he points out that there exists a family of statistical methods known as residual analysis that can discover trends and factors that might not be observed otherwise. Okay, so cold spray additive manufacturing is sort of particularly good to look at this because there's pretty extreme shear localization during the impact of that particle on the substrate. There's an adiabatic temperature rise. This leads to pretty big variation in the structure and therefore the mechanical properties. In fact, people have shown that even within a single splat, there is variation in the bonding and the mechanical characteristics, so let alone across a large surface area with many of these things. So why introduce this notion of stochastic plasticity? Well, this comes from a paper by lead author Brad Boyce and co-workers where they looked at using mechanical tests to actually extract out stochastic nature of the mechanical properties. The goal of this work is then to use residual analysis to do two things. First off, is to identify the influences of imperfections of the test conditions on the profilometry data to obtain during testing, and two, to determine the differences in variability between two different groups using test data. The test data they're going to use here is aluminum 7075 that's been cold sprayed. They got it from Solvis Global, and then they did 100 different indentation profiles. I'm going to show you the results of those in a second, but first, they point out that they expect there to be some variability. If you test it 100 times, it's never going to be the exact same. And the variability can come from different sources, like physical parameters, like the indenter load or the radial distance from the indentation center. Also from fitting parameters, like the average profile height, or nuisance factors like surface tilt not being exactly the same, or surface roughness, asphericity in the indenter, maybe it's changing as you indent it over time, or heterogeneous deformation behavior. All these things can lead to variability. And here you see the variability in these different profiles. Here we're seeing the depth of the indentation as you go radially outward from the indenter tip. Here's all 100 samples, and they're pretty close, but they're not the same, are they? Right? In fact, if you take the residual, in other words, each individual data set, and you subtract from that the average response, you see that some are outliers in the positive direction and some are outliers in the negative direction in this, Z, for example. So the idea behind this residual analysis is they're going to break it up into linear relationships between these different variability parameters, right? So here, for example, you're seeing principal component analysis where they're trying to explain what the variability could be coming from. Once they've figured that out, they can actually build a multivariate Gaussian model to simulate the same sort of variability that they're seeing experimentally. So in figure 11 here's an example of that. Here they have their synthetic profile variations generated from the different covariant structures considered in isolating the stochastic plasticity of this alloy, and they show you the variability from 50 different parameters. So what were their takeaways from this work? Well, right here they point out that, importantly, the rejection of measurement endemic nuisance error allows the approximation of the uncertainty associated with the material variability with more precision. In fact, there was a relative reduction of about 20% in the expected variation in the achieved set of profiles. And then secondly, they point out that residual analysis can actually be a method for validating the estimates in other uncertainty quantification as well as in multi-scale modeling. I hope you'll take a look about it. I think you'll learn quite a bit in the latest issue of IMMI.